This module is a transition module. We'll move away from specific computer languages like MATLAB and talk in general about how computers represent numbers and how arithmetic is done on a computer. A significant portion of the remainder of this course is about numerical algorithms for solving certain types of problems, such as numerical integration of a function, numerical differentiation, solving systems of linear equations, least squares minimization problems, solutions of ordinary differential equations, and so on. For that purpose, it's good to have an understanding of how computers represent numbers, how arithmetic is done, and what types of errors are made, and that's what this module is all about. We'll start by talking about representations of numbers. Numbers are the language we use to count things. Below I've drawn a picture of a bunch of objects. How many are there? And the answer is there's 9 or 9 in many other different representations. These really, at the core, are just familiar symbols that we use, agreeing on a common understanding of their meaning, to describe how many objects are there in that figure, without having to look at the figure once we've counted up the objects. But in a sense, these are just pictures as well. They're just representations that we've become so familiar and comfortable with. For me, the first two especially. So these representations on the right are different but equivalent representations that describe the number of objects in the picture. For two people or two parties or two parts of a computer program to communicate with number representations such as this, they need to agree on what representation system is being used. A computer needs to store numbers and operate on numbers, and to do that, it will have its own internal representation. That representation might not be the same as the representation that users are most comfortable using, so there needs to be a mechanism to convert between the internal representation and the representation familiar to users. Let's think a little bit about the representation of numbers on your computer. They're actually represented in several ways. Let's talk about the number 10.625. There's a visualization of it. I've got 10 and 5/8. For most of the numbers we work with, the actual internal representation in the computer is an ordered list of 64 elements, and these elements consist only of the digits 0 and 1. In that system, the representation of 10.625 is that 64-digit number of zeros and ones. The representation of negative 10.625 is almost the same, except the first 0 has switched to a 1. And the representation of 21.25 is like this. The circuitry in memory, the RAM, the hard disk, can store these types of representations, and the circuitry in the microprocessor can calculate with these types of representations. We won't talk too much about the technology of why computers use 2 digits for their internal representation. In this case, technology has converged to a point where it's very easy to build large, in fact incredibly huge numbers of circuits that can reliably store and differentiate between two things. We'll call those two things 0 and 1. They may be, in fact, a low voltage and a high voltage. In the computer and in the programs we use, there's many different number systems that are used. Therefore, there's actually different representations of the same number. The number 13 is visualized below. In one representation, it looks like this. In another very closely related representation, it looks like this. Another, again, closely related representation, it looks like this. And I can do that even one more time. And then in an alternate and quite a bit different representation called double, which you've now seen many times, its representation would look like this. Notice it's quite a bit different, and we'll discuss what all these things mean. Although we won't dwell on it, we do want to differentiate between a number's value, an intrinsic idea, and its representation. So for any number n, think of the picture of the 9 stars that represents the number 9. Let R of n comma s denote the representation using a standard s. And given a representation A, let V of AS denote the value using the interpretation of the standard S. If we take a number n and represent it using the standard S to get a representation, and then we compute the value of that representation interpreting the representation standard S, we should get n back. And the converse, for a representation A, converting it to a value using a standard, and then converting that value back to a representation using the same standard should yield the same representation. Here's some examples, kind of an abstract one. If we interpret the picture star as an intrinsic way of representing what we call 9 elements, then that is a number, and R of that number in the standard English is the word 9. Two that we'll use upcoming are base 2 arithmetic with a certain number of bits. Here we can take a number and convert it to its base 2 representation. We'll also talk about the IEEE double standard. In this line, we're converting a representation A using the IEEE double interpretation to a numerical value.